Well, this is it. This is the last section that we're going to be covering in this book for this course. But before we get started with the main point of this section, first the book presents a theorem that I think would have been better put in section 6.1. Mainly the theorem 6.3.1, if we have different eigenvalues of an n by n matrix with corresponding eigenvectors, then those eigenvectors are automatically independent. We're assuming here that these are actually non-zero eigenvectors. And it is very important that all these lambdas, these eigenvalues, are different from each other. If any of them are the same, this doesn't necessarily hold. So let's actually prove this. But the idea that even though the idea of the proof is pretty simple, it's a little tricky to set up. We're going to first assume that not all these vectors are linear independent. So we will pick the smallest, well, not the smallest, the largest number r. So we pick r. This is the largest such that x1 through xr are independent, but x1 through xr plus 1 are not. So because we're assuming here that r is smaller than k, there's going to have to be some point where it switches from them being independent to being dependent. So what does that actually mean? Well, that because these are not independent, there are c1 through cr plus 1, such that the linear combination is equal to 0, where not all of the c's are equal to 0. In fact, we cannot just have cr plus 1 not 0 and all the other ones 0, because xr plus 1 is not the 0 vector. So at least one of c1 through cr is not 0. Let's multiply this equation by a. And we can go ahead and just factor that a through the whole thing. Of course, a times 0 is still just 0. And here comes in the point that these are eigenvectors. All these x's are eigenvectors corresponding to certain eigenvalues. So a times x1 is just lambda 1 times x1. All the way through cr times a of xr is lambda r xr. And a times x sub r plus 1 is lambda r plus 1 xr plus 1. Okay, so what do we do with that? It looks very similar to what we had before, but now we've got lambdas in there. So putting in the lambda somehow doesn't change it from being 0 before to being 0 afterwards. What we're going to do is we're going to multiply this first equation that we started with by lambda r plus 1. And then we're going to subtract it from this equation here. So we're going to have a very similar formula that we have here, except now we're going to have lambda r plus 1 instead of all the other lambdas. It's an r, not an n. And when we subtract them, of course, we can go ahead and factor out the c1 and x1. We get lambda 1 minus lambda r plus 1. And we just keep going with that. We have cr and xr being able to be factored out, so we have lambda r minus lambda r plus 1. And then, of course, these two terms cancel each other out. They're gone. So what do we have here? This is a linear combination of the first r vectors. We have x1 through xr. The xr plus 1 is gone. And this linear combination equals 0. Since those are supposed to be independent, you'd expect all the coefficients here to have to be 0. But keep in mind, none of the c's are, well, sorry, I shouldn't say none of the c's are 0. There's at least one c that is not 0. So let's say that ci is not 0. But also, lambda I minus lambda r plus 1 is not 0. Why? Because lambda I and lambda r plus 1 are different eigenvalues. That was our condition. If they're different eigenvalues, then this is going to work. So if those are different, then their difference is not 0. So ci times lambda I minus lambda r plus 1 is not 0. That means that this is a linear combination where at least one of the coefficients is not equal to 0. And that's a contradiction. So if there's a contradiction here, we go back to what was our first assumption? Our first assumption was that not all of these were independent. So that cannot be correct anymore. So they have to be independent. So kind of a tricky little proof there, just because we're doing a proof by contradiction. If you're not familiar with doing proofs this way, that can be a little tricky to really digest maybe. But the point here is really the result. We're going to be using this result to actually prove something a little bit later. That's going to be kind of important. So let's go on to the main topic of this section. We've talked about similar matrices before. Remember that a similar matrix, so similar matrices, B is similar to A if there's some non-singular S such that B is equal to S inverse AS. And this was important because we can think of A and B as two matrix representations of the same linear operator, just using different bases. So this is very important for the theory of linear operators. But the natural question about this is, if we start with a matrix A, what is the simplest B that we can get? Or in other words, if we had a linear operator, can we find a basis for which the matrix representation is as simple as we can make it be? Well, what would be the simplest we could have? We would like it to get something as simple as a diagonal matrix. Remember, a diagonal matrix is a matrix that has potentially non-zero numbers along the main diagonal, but everything else is 0. So lots of zeros in here. The only things that are non-zero are along the main diagonal. Now, we do have to be careful here because not all diagonal matrices are similar to each other. We can't just get everything similar to an identity matrix, for instance. And why is that the case? Well, remember in 6.1, we proved that, I don't remember which number it is, but there's a theorem in 6.1 that we proved that says that similar matrices have the same eigenvalues. So if we have two matrices that have different eigenvalues, they cannot be similar to each other, but no matter what we do. So we definitely cannot get any diagonal matrix, because remember, if we have a diagonal matrix, the eigenvalues are literally just the diagonal elements, so lambda 1 through lambda n. Hence why I'm using lambda for my diagonal matrix. So we want to see, well, if we have if we identify the eigenvalues of a matrix, can we turn that into a can we say that that matrix is then similar to a diagonal matrix using those eigenvalues? Well, if that is possible, we say that A is diagonalizable. So it's just basically saying that it's diagonalizable if there's a non-singular matrix X and a diagonal matrix D such that X inverse AX equals D. So the X here is the S we had before, and the D is playing the role of B from before. We say that the X matrix actually diagonalizes A. But not every matrix is diagonalizable. And in fact, by proving the theorem 6.3.2 that says a matrix is diagonalizable if and only if A has in here, A being an n by n matrix, if and only if it has n linear independent eigenvectors, by proving this theorem, we will actually be able to find a way of constructing what X and D actually are. So, kind of, you probably already see here that D is going to be the matrix with the eigenvalues. But how do we get the matrix X? It's actually not as complicated as you might think. So let's assume here A has eigenvalues lambda 1 through lambda n. Here I'm not actually assuming that these are necessarily different, but we are going to say we have eigenvectors x1 through xn. We're going to assume that these are all independent, and each of these corresponds to the same number eigenvalue. So maybe lambda 1, lambda 2 are both 1, and so x1 and x2 are both eigenvectors corresponding to 1, but we're assuming here that they are still independent from each other. So we can't guarantee that just from knowing that 1 is, say, a multiplicity 2 eigenvalue, that we can get x1 and x2 they're independent. But here we are going to assume that we already know that to be true. We're going to make our matrix D, just like before, so just putting all the lambdas into our matrix like that, a diagonal matrix with all the lambdas along the diagonal. And we're going to make a matrix X, and we're just going to take the vectors x1 through xn. So these are column vectors. We're going to just put them as columns of a matrix. And the important thing here is if we take A times X, what happens? Well, because of the way we define matrix multiplication, what we can do is essentially apply A to each one of those columns. The first column of this product will be A times X1. The last column of this product will be A times Xn. Since x1 through xn are eigenvectors corresponding to eigenvalues lambda 1 through lambda n, then A times x1 is lambda 1 times x1. A times xn is lambda n xn. And it shouldn't be too hard to see that this is actually the product of X with the diagonal matrix D. If you just work it out, you can see that this actually works out very nicely. So here we actually do have AX equals XD. We know that X is a non-singular matrix because we're assuming that these eigenvectors x1 through xn are independent. So this is a matrix with independent columns, a square matrix with independent columns. And so we can just essentially multiply the inverse of x to the other side and have that D equals x inverse AX. Exactly what we want it to be, that A is diagonalizable. And of course, we can go the other way. If we have this kind of formula here, we turn into ax equals xd. Well, ax is this product here, where the x1 through xn are the columns, and xd is this product here. That means that ax1 equals lambda 1x1, and so on and so forth. And so the x1 through xn turn out to be the eigenvectors corresponding to these lambdas being the eigenvalues for A, and they have to be independent because we're assuming here that x was actually non-singular. So this actually goes very easily goes both ways. But the point here is to see if something is diagonalizable and to even find the diagonalizing matrix. All we have to do is what we were doing in 6.1. We're finding eigenvalues and eigenvectors. And once we do that, we're good. Our results about this are kind of summarized here. The first one comes straight from our proof, that if we have the columns of our diagonalizing matrix are eigenvectors of A, and the diagonal elements of D are the corresponding eigenvalues. That's kind of what we just said. Number 2 is saying that if we reorder the x's, so if we reorder the columns of the matrix X, all we're really doing is changing what our numbering system for the eigenvalues and eigenvectors are. It doesn't really change too much about the process. And so what exactly X is not very unique. In fact, we could also even pick different eigenvectors corresponding to the eigenvalues that we know of and get a new matrix there that even has different different columns than the X that we were working with. So there are multiple answers here, but they'll be pretty much. It's pretty easy to tell when. When we're doing the problems, it'll be pretty easy to tell which ones are probably the best to use. So we'll go through problems after this point. I want to get through the theory behind this before we get into that. The third one here says that if we have indifferent eigenvalues, here A being an n by n matrix, if it has indifferent eigenvalues, then remember our first theorem. Our theorem says that since all those eigenvalues have a non-zero eigenvector, and there's n different ones of one of those, then each of those n eigenvectors are independent. And so, because of that, we have indifferent eigenvectors that are independent. And so, by our theorem 6.3.2, the matrix is diagonalizable. So, the best case scenario, the best scenario that we have is when we just have indifferent eigenvalues. It's when we have repeated eigenvalues that we either have to find more than one eigenvector corresponding to the repeated eigenvalues, or we might not be diagonalizable. And in fact, remember what it means to not be diagonalizable, meaning that we don't have indifferent eigenvectors. We call it such a matrix defective. So that's kind of why we use in that term. A defective matrix is one that we cannot do this process on. Things break. We can't diagonalize it. All that kind of stuff. But that's why we use that term. And I've been using it throughout the last few sections. So hopefully by this point you're familiar enough with it, even though technically the book defines it in this section. Finally, we have part 4, which seems kind of weird. Why are they stating this? All we're really doing here is remember, we have our d equals x inverse ax, and they're turning that around, just moving the x's over to the other side and saying that a equals xd x inverse. Why do we have both these? Well, we actually mentioned this because having this way of writing a in terms of a diagonal matrix and x, it can make some stuff easier. For instance, what is a squared? Well, this is just a times a, but a is equal to this. So we just multiply that to itself. Of course, here the x inverse and the x can cancel each other out. Then we just have the, well, they cancel each other out by turning into the identity matrix. We have d times d in the middle now, but we have x times d squared, x inverse. In fact, you can keep going with this. If you have a whole bunch of powers of a, then it turns into x d to that same power times x inverse. And this is very important because what is the power of a diagonal matrix? We have our diagonal matrix with our lambdas to the nth power. Multiply all those together, you just get lambda 1 to the n through lambda n, or I should probably not use n here. Let's change this to k. Using don't want to use the same as the size of the matrix. So here, just any power doesn't have to be the same as the size of the matrix. But we just take all of our lambdas and take them to the same power. And so it's really easy to get this power in the middle. We already know what x and, well, hopefully we know what x inverse is. That's probably the trickiest part of the computation, really. And then finding the power, any power of A, is just as simple as multiplying together those three matrices. This can be very helpful because finding powers of matrices is not really all that straightforward a lot of the time. This actually even works with inverses. A inverse is going to equal x d inverse x inverse. And kind of the same formula. The inverse of the diagonal matrix. And you can even think of this as now as a power. The inverse, we can bring that -1 and put it as a power on all of those. Or in other words, our diagonal elements are 1 over lambda through 1 over lambda n. Now, whether or not this is simpler, because we do have to still find x inverse, is a whole nother matter. We still have to find the inverse of a n by n matrix. Though there might be other ways of getting a hold of that matrix. Alright, so in interest of time, I'm going to go ahead and cut it here and make an examples video where we'll diagonalize some matrices. After that, we are going to then apply this to another kind of problem. That'll be in our third video. That will kind of go back to what we're talking about in 6.2 and all the systems of differential equations. So I'll see you in that next video.